Hi, I'm Daisuke Iwai. I'm going to introduce a new projector intrinsic calibration technique that does not suffer from a shallow depth of field problem of a projector. So this work was done mainly by my student, Masatoki Sugimoto, and my colleagues. Projector intrinsic calibration is essentially same as a camera calibration method based on a pinhole camera model, because the projector and the camera share the same optical mechanism except the light directions. Specifically, we obtain a number of correspondences between 2D projector image coordinates and 3D world coordinates by projecting structured light patterns onto a checkerboard and calibrated the projector using the correspondences. However, this method only works as long as the projected pattern appears focused on the board. Normally, projector's aperture is designed to be wide to achieve a bright projection, and thus the depth of field is normally very shallow. When a projection target locates near the projector, we can use a handy calibration board and move it easily in front of the projector. On the other hand, when the target locates far from the projector, we need to prepare a large board to cover the projector's field of view at the target location, where the projected pattern is focused. The calibration board potentially becomes too large to move by a human operator, and in that case, the projector intrinsic calibration becomes difficult. We propose a new projector intrinsic calibration method by directionally decomposing structured light. Our calibration device consists of pinhole array masks and a flatbed scanner. We project structured light patterns to the device, which decomposes the projected light. And our technique virtually converts a projector of arbitrary aperture sizes and focusing distances to a pinhole projector. Therefore, our method does not suffer from the shallow DOF problem. Here, I explain how to decompose the projected light and how to use it for the calibration. Suppose a single pixel emits a light. The light rays emitted from the pixel diffracted at the lens, and among them, only a ray passing through a pinhole reaches the scanner surface. Light rays emitted from other pixels also pass through this pinhole. And consequently, these rays form a blob on the scanner surface. Among these rays, we extract the chief ray, which passes through the optical center of the projection lens. The chief ray can be regarded to be projected from a pinhole projector, and thus we can obtain the 2D and 3D correspondences required for the projector calibration. So this is our chief ray extraction technique. Unfortunately, the blob center does not correspond to the chief ray pixel. Therefore, instead of extracting the chief ray pixel in this blob, we determine it on the projector's imaging plane. We found that the blob pixels form a true circle on the projector's imaging plane, and its center corresponds to the chief ray pixel. Please refer to the paper for the details of the proof. So in summary, our calibration process consists of the following 3 steps. First, we project structured light pattern from a projector to the calibration device. Then we extract the chief ray pixel for each blob on the scanner surface. And finally, we calibrate the projector using the 2D chief ray pixel coordinate on the projector's imaging plane, the 3D coordinate of the pinhole through which the chief ray passes, and the 3D coordinate of the chief ray pixel on the scanner surface. So we built a prototype using 2 pinhole array masks as shown here. When we project a fringe pattern, we can see blobs on the pattern, blob of the pattern on the scanner surface. On the other hand, because the device is placed close to the projector, the projected fringe pattern is not shown on the mask due to the defocus blur. So this movie shows the scanning of projected gray code patterns. So I guess it might have been already seen in the movie. The projected pattern was clearly visible in the scanned image when the pinhole array masks was used. On the other hand, the high frequency components of the pattern was significantly reduced due to the defocus blur when the pinhole array masks was not used. This shows a result of the chief ray pixel extraction. We compute the chief ray pixel by fitting a circle to the blob on the projector's imaging plane. So we confirmed that the extracted chief ray pixel was not identical to the blob center in the scanner image. We conducted a calibration experiment using 3 types of projectors with 3 different aperture sizes. We set 2 focusing distances, 1 meter and 3 meters for each projector. We compared our method with a conventional projector calibration technique. In particular, we projected a black and white checker pattern onto a yellow and white checkerboard and captured it using a camera. The printed yellow and white pattern was used to calibrate the camera, and the projected pattern was used to calibrate the projector. The 2 patterns were separated using different color channels. In the near condition, the calibration board was small so that the experimenter could change its pose relative to the projector. In the far condition, on the other hand, the board was too large to move by the experimenter. So we moved the projector to change the pose relationship instead of the board. This table shows the calibrated parameters. Let me briefly summarize the result. So first, when the experimenter calibrated one of the projectors, it was too heavy to move in the far condition, and thus there was no calibration result. On the other hand, our method could calibrate it. Second, the focal length and the x-coordinate of the principal point were similar between the proposed and conventional methods. On the other hand, the y-coordinate of the principal point was largely different between the methods, because in general, this value is not stably calibrated in a projector calibration due to the off-axis property of normal projectors. Nevertheless, the reprojection error was less than 1 pixel in all the cases, and therefore the calibrated parameters do not seem to be significantly bad. We evaluated the calibration accuracy in a pose estimation experiment. So specifically, we estimated a projector's pose relative to the large calibration board using the calibrated intrinsic parameters and 2D to 3D coordinates correspondences between the projector and the board at the 4 corners indicated by the red arrows. When we then computed the projector coordinates at the other checker corners and projected white dot at the computed positions, we measured the distance between the projected dot and the corresponding checker corner. The graphs show the mean and standard deviation of the measured distances. A paired t-test does not show any significant difference for every pair, and thus we confirmed that the proposed method could calibrate the projector at the comparable accuracy with the conventional method. We confirmed that the estimated intrinsic parameters realized a relatively large-scale dynamic projection mapping application. So we estimated the pose of the projector in the world coordinate system with the intrinsic parameters and manually obtained 4 correspondences between the projector image coordinate and the world coordinate. In conclusion, we realized projector intrinsic calibration that does not suffer from the shallow DOF limitation. As a future work, we are interested in speeding up the calibration process using a camera instead of a scanner. Thank you very much.